now. Great. Okay, now let me share the screen and then we can go with that. Great. So let's do this one, this, good. So we are still talking about streaming algorithms. And again, in the streaming algorithm, we had this idea that make sure, yeah, good. And in the streaming algorithm, we had this concept that like a set of big data are coming in a stream. And in particular, it can be a set of numbers that we are seeing them, or a set of edges of a graph. And that you can, for example, see it in some API calls. So API calls are some of the things that currently is used a lot in practice. And then you are just inserting this number. So these numbers coming one by one, and we don't have memory to have everything there. And we want to get some high quality solutions. And that will be a streaming algorithm that we are considering. Now, we discussed about some hardness. In particular, we talk about two important problems that we discussed. And both of them are important ones that we have discussed. So this is the index problem that for which Alice has a string of length n, and Bob has a natural number. And the idea is that we want to compute x of I. And this is a one-way communication that Alice should send some information to Bob. The other problem is a disjointness problem that now it is more symmetric. Alice and Bob, both of them have strings of length n, and they want to see whether there is an index I such that both of them are equal to 1. We call it disjointness because if you consider those places that xi is equal to 1 is a set and yi equal to 1 is a set, and you want to say whether these two sets have any intersection or not. Both of these problems, as we discussed, they need order in communication. Disjointness, it works even for multi-round communications. So it means that Alice can send something to Bob, Bob can send some to Alice. But the important thing is that the total communication that we need should be at least omega n for both of them. And we discussed about a particular problem, maximum connectivity, maximum connected component, K, whether there is a connected component of size at least K for a K greater than 3G. And we talk how can we, this was the idea to, how can we get a reduction from index to this problem. The idea is that we need to solve the index to this problem. And the idea is that these two guys, they are just building some graph, and then they are giving to the algorithm. And at some point, when Alice sends her edges to the algorithm and runs the algorithm, the space, the memory would be the bits that Alice will send it to. That was the main idea. And we said that if at that time the size of the memory is less than omega n, then that's a contradiction for index. This is some kind of information theoretic bound for index. Now we are continuing this, and we are seeing a few more problems on that things. And good. So the next problem that we want to talk here is the problem of a very simple graph, a simple problem as we mentioned before. You are given a graph, and you want to see whether G is a tree or not. So of course, in this case, one problem that we can do, we can count the number of edges. Number of edges. And one thing which is important here, we are assuming that no edges will be repeated. So counting the number of edges would be easy. You can just do it order like n. correct? Because you need to have a counter to just count the number of edges, and assume that, as I mentioned, no repeated edges here. And note that again, we are talking about lower bounds. So in the lower bound, if you put some conditions there, it would be better. So you want to say that even this special case of problem cannot be solved. So counting, you can count the number of edges by order log n, and just make sure that the number of edges that you will get should be n minus 1. Say n is given also in advance to you. So even you know n as well. So you will check it, the number is n minus 1. But the issue is that if there are n minus 1, there is no necessity that the graph be actually 3. A good example is this one. For example, you may consider this one, that is this graph that I'm giving. And here, you can see that this graph, for example, has 3 edges and 4 vertices, but it's not a tree because it has a cycle. This is the problem. So we want to say that this problem, of course, one way is to, for tree, there are actually, if you want to use order n space, there are algorithms to do that. And like one way you want to make sure that if this is the graph is connected and it has n minus 1 edges, then this graph is a tree. But yeah.
So if it's hard to check whether it's a tree, does it also mean that it's hard to check whether it's connected? Because
yes, exactly. So that's actually the connectivity part. So the connectivity part, actually, there are algorithms that for connectivity, you can do it n log n. I think even something like this. I think this is a paper by David Woodruff. If you search, you will find it for connectivity. You can do it n log n space, but here everything is in terms of a space. Here, what do we want to prove? We want to say that you cannot do this one sublinear in n. That's the thing that we want to prove. So we want to say that this problem is as hard as like index, and it means that this is the main thing. This is the main theorem. Any single path protocol for this is for index same, and this is the other one. Any single path streaming algorithm solving is tree needs order n space. So that's the main theorem that we want to prove. But for this, we are first proving this temporary theorem, or like this lemma in some sense. So for this one, we need to introduce another problem called index same. That's actually a useful problem. This is like we talk about the tree sum, and then we had the tree sum prime. You can say index same is somehow index prime. So what is the problem? So Alice has a string. Let Alice have a string x, and Bob have a number I. So the same thing as index. The only thing is that I belongs to is 0 to n minus 1. Okay. Now, the question is that Bob wants to compute this index same problem. What is index same? Are there two essentially consecutive bits which are equal? So this is the main thing. So this x that is given to us, for example, if 0, 1, 0, 1, 0, 1, in this case, there is no index that two bits are equal. But if we have such a thing like this, then this is for this guy, we have two bits which are equal. Good. So index same is the one that's asking whether there are essentially I and I plus 1 which are equal. And of course, if they are both 0, also that counts. So, and here we want to say that, and again, this is by same strategy. It's like one-way communication. Alice needs to send some information to. We want to say that first, this problem is as hard as the index problem. So this is the theorem that we want to prove, that any single path protocol for index same needs order n memory. And then we are using it. So first we are saying essentially a reduction from index to index same, and then from index same to is3 problem. So how can we have a reduction from index to index same? So that's actually simple. So consider the string essentially. We are creating so this is the string essentially for X, for index to Xn. So this is for index. Now create this string. So we are creating strings of length 2 times n actually. Now, what do we do here? This is X prime that we are creating. And it has, say, X prime 1 to X prime 2. Okay, how do we do that? We are just putting this one. So actually this is X to n, but each of these Xi's has 2 bits. So the total length would be 2n. So X prime I, it is equal to 0, 1 if Xi is equal to 0, and it would be equal to 1, 1 if Xi is equal to 1. Good. Now, just as I mentioned, the length of this string would be twice the length of the original one. Well, of course, within a factor 2, nothing will change. Now, it is easy to see that index Xi is equal to 1 if and only if index same of X prime and I prime is equal to 1. Here, I prime is actually twice times I for this I. So for I prime, which is 2 times I minus 1 plus 1, X of I is equal to 1 if and only if X index same of X prime and I prime is equal to 1. Why? I mean, this is actually the idea is simple. Because if this guy is equal to, so this 2I comes essentially from the fact that each Xi goes to strings of length 2 here. And then it would be 1 if, of course, in this case, index same would be 1. But the other case is that the only thing that we can have it. So if we have a set of zeros, index same will not become to 1 because it is 0, 1. Not 2 of them are equal. So the only way to make it essentially index same equal to 1 is that you will have 2 1s. Does it make sense? Any questions? Good. So that's a step by step. So we have now index same problem, which is as hard as index. Now we want to use that one and say that any single path streaming algorithm solving history needs order n space. Good. So let's clear everything. Good. So the strategy of proof is very similar to the previous theorem that we have. We talk about the maximum connected cases. We are using a reduction from index same to history. First, we need to create a graph and say what are the edges of Alice, what are the edges of Bob, and then we are giving the edges of Alice first to the algorithm, and Alice runs the algorithm on that, such that at the end of that phase, the memory that Alice has from the algorithm, that will be the set of bits that it will send it to Bob. And if Bob can continue this algorithm because they know the algorithm A as a part of this public protocol. Then continue the algorithm A to compute the answer. And at that time, we can have the answer of is 3, and it is corresponding somehow to index same. Then we should have this property that the total bits that Alice sends to Bob should be at least omega n. So let's create this graph G. We start with a set of vertices V. So V would be 0, 1, and then 1 to n. These are two special vertices. And of course, the set of edges would be like previous case, E of Alice and E of Bob. Good. Now, what is E of Bob is very simple. The edge from I to I plus 1. That is the index I that Bob wants to see whether it is 0 or 1. What about for Alice? So for Alice would be this. It would be like I to 0 if xi equal to 0. So what is the index same problem? Index same problem essentially again. Now we have given the x1 to xn. Now each of these this x1 either it is 0 or 1. If it is 0, then at that I, particular I, so for example here you consider I again. So if this I guy is 0, then we connect I to 0. So 0 was the vertex. And if I is equal to 1, so if that is if xi equal to 0. And otherwise, xi equal to should be 1. If xi equal to 1. Good. So that's a graph that we have. It's a very simple graph. And how many? There are n edges here, so we have n vertices here. Good. So in total, how many edges do we have? I mean, we have how many vertices and edges? We have n plus 2 vertices because we have 0, 1, and 1, 2. So it is n plus 2. How many edges do we have? So here we have n edges for Alice and 1 edge for Bob. So we have n plus 1 edges as well. So because the graph has n plus 2 vertices and n plus 1 edges, it means that either the graph is a tree or it should have a cycle. Now, this is the main question, the main claim that we are doing, and that's it. So that would be is 3 of G is equal to yes, if and only if index same of xi is equal to 0. Why? This is the example, actually, we can see that. So the only way that we can have a cycle is that there are 2 of these guys, because here, note that there is no edges here. So these guys are just either connected to 1 or 0. In that sense, there is no cycle in the graph. The only case that we can have a cycle is that if one of them, like 2 and 3, both of them are 1. In this case, because there is an I guy here, then we have a cycle. Or both of them are equal to 0. That's also another case. Then in this case, we have a cycle. Otherwise, if one of them is 0 and one of them is 1, as you can see it here, for example, if 2 is equal to 1 and this guy is equal to 0, this just connects these 2 parts of the graph. essentially this connects 0 and 1, because if there is a cycle, it means that the zeros and ones will be not connected. But if there is one of them is 0, one of them is 1, actually just connect zeros to ones, and the graph would be a tree. So we have this if and only if part. And again, what would be the strategy? So we have created these edges of Alice, edges of Bob, and the actual reduction is that first Alice gives the set of edges that she has, and then first actually consider those edges, runs this algorithm A on the set of edges that she has, and then at that time when it ends, then see what is the memory of this algorithm A. This is the memory that it will send it to Bob. And then Bob continues the algorithm because it knows the algorithm, it knows the memory. So, and the memory is a sketch of everything that it needs to know. It continues the algorithm with a set of edges that he has, in this case, only one edge. And then at that time, decide whether so assume that, I mean, there is an algorithm that needs like a less than n space. Then at that time, it can decide whether this graph is a tree or not. But if it is a tree or not, that decides whether index same is 0 or 1. And in that case, it means that we can always solve the index same problem with little of n spaces, which we know that is impossible because index same, which is equivalent of index, for this problem we cannot. That's the whole algorithm, and that's the thing that we were discussing. So I don't repeat this one for the future problem. I just want to repeat it once such that you remember what is the idea. Because this is a bit different from the regular reductions. We are going from a streaming algorithm and memory, we are going to talk about the communication complexity. Any questions? Okay, is everything clear? Good. Let's go to the next problem. Good. So this is another problem, a 3 diameter K. Let's G be a 3. Is the diameter of G is at least K greater than or equal to 3. Again, this is called promise problem, that you know it is a 3. So adversary guarantees that it is a 3. So it has n-1 edges and it is a 3. Then the question is whether the diameter of G is at least K greater than or equal to 3. So this is a good exercise that you can prove that any single path streaming algorithm for a 3 diameter K needs order n memory. This can be actually, you can see also the maximum connected component that would be similar to these two. You can just think about it and get it. Okay. Now let's go to another problem, which is interesting, the perfect matching problem. So what is the perfect matching problem? So so you are given a graph G, and you want to see whether there is a perfect matching in G or not. So let's just define what is the perfect matching here. So a perfect matching, essentially, as we discussed before, a matching is just a set of edges that no two of them share a vertex. So this should be not the case, the matching. And the perfect matching is the one that essentially, when you consider this set of edges in the matching, that all vertices in the graph are essentially matched with one other vertex. So all vertices are matched. Good. So here, all vertices should be matched. That's the meaning of a perfect match. Perfect match. Good. So that's a perfect matching, meaning that all vertices should be matched. Now, you want to say that this is the theorem that you want to prove. Any single pass streaming algorithm for perfect matching needs at least order of M memory, which, I mean, in particular case that we have it, we are proving actually for the case that M can be order n square. So it needs n square memory. Okay, so how can we do that? So we are getting another reduction from index problem. So assume that now X, so X generally so far was just essentially one-dimensional array. Assume that now X is a two-dimensional array. So X is a n by n array. And Bob wants to know X of I. Which is the index of, okay. So now this is the interesting thing. Because here we are assuming X essentially. So instead of essentially putting X like this, we are putting X like this. Good. So instead of X that we had it before, so we are just put it, I mean, essentially as a two-dimensional thing. If you are using actually Python, you can reshape the array or make the shape essentially instead of linear, you just put it n by n. Now, index problem here would be, before we wanted to get X of I here, but here, in this case, when we make it essentially this kind of two-dimensional, we want to get X of ij, which is n by n. So the total length here would be n squared. So here would be n squared, here would be n times. So we know that if we have n squared as the x things, according to index, we need to have omega n squared bits are sent in a one-way communication from Alice. Good. Now, but we want to solve the index problem using this matching problem. So again, we need to create a graph. So what is the graph? Again, the set of edges of Alice and set of edges of. So let's create essentially this graph. So so for this part, for this set of edges 1, so we have n by n. So any edge, if xij, so eij belongs to E if and only if xij is equal to 1. So for any edges that exist in the graph, you are putting an edge from here. Good. So that is essentially, these are the set of edges from 1 to n. So essentially from this xij, any edges that exist between I and j, we are putting an edge between I and j here. Now, we have another set of edges. So this is the set of edges 1. And this is actually the Alice's edges. So this is the regular, because we are just encoding this string as this bipartite graph. So this 1 would be for Alice. Good. So all edges here, in this case, these are the Alice's edges. again, xij is equal to 1 if and only if like there's an edge between I here and j here, if and only if xij is equal to 1. That's the thing that we have. Now, what about the set of edges 2? So what is Bob? Bob wants to know the. So Bob wants to know. So let me write this one. Bob wants to know xij now, correct? Instead of just xi, that was the linear case, it wants to know ij. So how do we decide about this ij? So you have, in addition of these n vertices here, so we had n vertices here and n vertices here that we essentially encoded Alice's string here. Now, we are adding n minus 1 edges here, n minus 1 vertices here, and n minus vertices here. So this ij that Bob had it, so here, what are the set of edges that we are putting in set edge 2 that Bob has it? Here, these are n minus 1, these are n. I will create a perfect matching, and this guy will be connected to everyone here except for I. So these n minus 1 guys that we have it here, they will be connected to these n guys, except the only one that is not connected is I. What is this I? This I is the same I that we talked here. Similarly, for the other part, we have n minus 1 vertices in the other side, and these guys are connected all to these n vertices except for j. So this j again is the same j here. So what is the idea? The idea is that if we have, so this graph has a perfect matching if and only if this guy has an edge between them. Because if this guy has the perfect, if this guy is 1, then we can match all these guys to here. And all these guys to here. So here essentially says, and that's the only way that you can have a perfect matching, because otherwise I and j, they don't have any other edges attached to them.
I and j can have other edges.
Yeah, they can have actually other edges attached to them. Yes, exactly. So that's actually this one. Thanks for correction. Yes. So here, these edges, so the proof would be like this. These edges here in the side guys, these guys and these guys, they don't have any other edges attached to them. So they are forced to take those edges that are attached to them in a perfect matching. So it means that the only guy that does not have any edge attached to that, so in the matching one, everyone gets matched except j here and I here. Now, if xij is equal to 1, so if essentially xij equal to 1, if and only if there is a perfect match. So again, so these are, and this set of edges, these two guys are the two, let me just change the color. These are the Bob's edges. These are Bob's. Good. So this is the way that we create this graph. So for ij, here, ij, there is no edge is connected to them from this kind of side nodes. And if you have a perfect matching, because the side nodes, they need to be connected, essentially be matched. The only way is to match with these guys, with the middle vertices. But then in this case, only I and j, they don't have any edge connected to them. And the only way for them to get matched is that there is an edge between ij such that they can match. This graph has a perfect matching if and only if xij is equal to. So that essentially proves that this problem is as hard as the index. Again, why? Because we are giving the set of edges of Alice, which is in this case the edge set 1. And then Alice computes the memory at that time and then gives that memory to Bob such that Bob runs on his set of edges, which is in this case is set of edges 2. And at the end, if there is a perfect matching, it means that the graph, the xij was equal to 1, otherwise it would be 0. It means that the total memory that Alice has sent to Bob should be at least omega n square by the index problem and cannot be less than. So this algorithm needs at least omega n square essentially. Memory. Good. So that's the way that we could do it for perfect matching. Now, a very similar things also you can show the shortest path problem. So what is this problem? So let me say this one. We are using exactly the same graph. What is the length of the shortest path from V to W? So you are given a graph and the shortest path problem VW said that what is the length of the shortest path from V to W? Here, we actually prove something even about approximation. We said that you cannot approximate this one better than 5/3 unless the memory that you have it is omega n square. So we want to say that you cannot even approximate it better than 5/3, not let alone the exact solution. Even the approximate solution, you cannot get better than 5/3 unless you have omega n square. So what is the thing? So the proof is exactly like the construction is exactly the one that we created for. So you are given a graph G. The construction is exactly the one that we created above. So these are the set of, I mean, actually not exactly, it is almost like the same one. So here, in some sense, all these guys that we had it here, so yeah, let me repeat that, that would be better. So here, what do? We have this graph, essentially this vertex V here. This is the graph that we're creating. This is V here. This is W here. Now, what do we do from, we have n vertices here, n vertices here. So we are, again, considering a two-dimensional case of index. Now, V is connected to every guy here. Sorry, just actually that was not right. Yes. Yeah. So here, I mean, this is the vertex V. This is the vertex W. We have this this part. This it is exactly the one that we discussed here. So these two would be exactly the same thing. Xij would be equal to 1 if and only if there if and only if there's an edge between these two guys. Now, from what about the index of Bob? So if Bob, again, index was Xij, so I'm adding an edge from V to I here and from J to W here. So except that, so this part, as I mentioned, this middle part is the same as this middle part here that we discussed. So again, Xij is equal to 1 if and only if there's an edge between these guys. Now, what is index of Ij? So this is this I. V is only connected to this I. And W is only connected to J here. And the set of edges, again, 1 is the middle guys and 2 this I. And these are here essentially only 2 edges in the set edges. Again, 1 is for Alice. And 2 are for Bob. Good. So these are Alice's edges and these are Bob edges. Now, what is the catch? So the catch that if there is if xij is equal to if xij is equal to 1, then there is a path of length 3 from V to J. Then there is a path of length 3 from V to W. So why? Because I mean, you come to I, then it is xij is equal to 1. You will come here, and then you will go there. However, if xij is not equal to 1, then the only way that you can do it is that you cannot. So when you come here, this guy is not connected to this guy. So you need to go here. That's right. So you will come here. Then you cannot go directly to this guy because these guys are not connected. So in that case, you need to go here at least to one vertex, and then here, and then here. That's the only way that you can get connected. What is the length of this path? You can unmute and answer.
5.
Yeah, it would be at least 5. So, and that's enough for us. So if xij is equal to 1, there is a path of length 3. If not, at least 5. 5 is the length of the path from V to I. So it means that between these two cases, whether it is 3 or 5 or greater than 5, it would be the case that you can distinguish whether xij is equal to 1 or 0. So it means that if you can get better than 5 over 3 approximation for this problem, so if you get better than 5 over 3 approximation, so what's the meaning of that? Say the approximation is less than 5 over 3. Then you will just multiply 5. So in some sense, so if the approximation is less than 5 over 3, so in that case, if the algorithm reports, it is an approximate algorithm. If it reports the length of the path is less than 5, it means that it should be 3. So then you know that xij is equal to 1. However, if it is 5 or greater than 5, then you know that in that case, because you know the approximation is at most less than 5 over 3. So if this one is like the approximation length is less than, is like essentially 5, because the approximation guarantee is less than 5 over 3, it means that the length of the path definitely should be greater than 3. And if it is greater than 3, of course, it means then it should be 5, but in that case means the xij is equal to 0. That's the way that we are doing essentially for approximation, that if two cases are hard between 5 and 3, we can distinguish. It generally means that 5 over 3 is you cannot get even any approximation better than 5 over 3. You are using this for other things. Good. Let's go and see another problem. So far we have just mainly used this index problem. However, lots of this problem actually you can get from disjointness as well, very similar things, and get even say that even if you are doing multi-rounds, or like in this case would be multi-pass, still you cannot get anything better than order n space. So let's see one problem, for example, here for the disjointness. So we want to use now disjointness and the frequency problem. So what was the frequency moment problem? So here you are given a data stream. You are given a data stream y1 to yn. Each yi is belong to 0 to m, essentially. So the range of yi would be 0 to m minus 1 or 1 to m. And the frequency of one I belongs to one, like in this range, is the number of xi's, which would be essentially xi, which is equal to the number of yi's that are equal to I. So here, these are the numbers essentially are coming. So 0, 1, 2, 0, 3, 1. This is a set of numbers. So here the numbers are between, say, 0 to 4. So the numbers between 0 4, there are m numbers, say m is equal to 4. This is the string is coming. And then you want to say, what is the frequency of x? What is the frequency of x0 here? Or what is the x0, which is the frequency of 0 here? Is 2, because there are two numbers which are equal to 0. What about the frequency of x1? Like, not the frequency. What about the frequency of 1? 2 again. For what about x2 is equal to 1, and for 3 is equal to 1. So these xi's are called frequencies. So this is this strings of length n is, so the length of this string is n, but here these are the numbers from 0 to m, 0 to m, but m is the open thing, so this is m here is equal to 4. So the numbers in the range of 0, the n numbers are coming, each of them from the range 0 to m minus 1, and you want to say that from each number, how many appeared in this string. Now, this is the problem. The piece for any piece frequency moment of the input is defined as follows: f of p is equal to this. If p equal to 0, would be just So if f of 0 is the number of distinct elements in the string. Good. So we compute essentially this frequencies, which are x1, x0, x1, x2. These are just a number of zeros, number of ones. Now, we want to compute essentially the, and this xi is called the frequency vector. This has the opposite. But you have the question? Now, the piece frequency moment, so this is the frequency moment essentially, is equal to this. So if p is equal to 0, would be number of i's that x i's is not equal to 0. What's the meaning of that? It means that the number of distinct elements in this. F1 would be just the number of elements, because just sum of all xi's. Sum of all xi's would be the number of elements, would be n. So F1 would be essentially n. So if p equal to 0, it would be, as I mentioned, then the number of distinct elements that you have. If p is equal to infinity, this is essentially comes from the norm. In this case, would be just the maximum xi. Who is, like, which number appears the most? Otherwise, it would be like the frequency of p would be xi to the p, sum of xi to the p. This, in some sense, this is the more general, this is the norm that we are doing that. Yeah. So this is XP. So when you have a norm, then you have a. So generally, when you have if you have just XP, norm P, then you have everything to the power of P, and then you need to take the root P. But here, because it is to the power of P, then we don't have this P anymore. We don't have this. We have just Xi to the P.
If you have the root, it is the same problem, right? You can just take the root.
Yeah, exactly. It is no problem. So you can, of course, you can just take the root and then just do that. Just cleaner things.
And I guess max of Xi is like because of
exactly. Yeah. So in some sense, these two are also special cases of this. I mentioned it here to be, things, but actually when you define this XP, X infinity, it exactly means max I essentially. So when P is infinity with such a formulation, then it means that it's max I. And if P equal to 0 would be essentially this definition. Because here would be exactly Xi to the 0. So 0 means those guys that are, if Xi is greater than 0, then this would be 1 and you will count it. Otherwise, the issue that 0 to the power of 0, you want to define it as 0. That's the thing that you are defining. If you define that way, then actually this one, even for P equal to 0, you get this. But this is essentially the main problem that we want to solve it. Xi to the P for any P. For different P's actually give interesting numbers. For P equal to 0, gives a number of distinct elements. For P equal to 1, it says that number of elements, and for P infinity means maximum. And here, they prove actually this in this paper, several of these interesting results. Good. Good. So what are these ones? So this is the paper by Indick and Woodruff that they prove it in, it was in 2005. They prove, very interesting thing. So they say that for P, if P, between 0 and 2, there is a randomized streaming algorithm that computes 1 plus epsilon approximate solution for f of P, the P's frequency moment, in a space polylog Mn. So if P is between 0 and 2, and again, P here can be any fractional number as well, anything between 0 and 2. Then you can compute in polylog M. So in that case, actually, that's a good case. Because it is polylog. As I mentioned, polylog is the somehow ideal case. Because even a counter needs log n bits. However, if P is greater than 2, any randomized streaming algorithm that approximates f of P requires m to the 1 minus 2 over P. And actually, for P greater than 2, there is a randomized streaming algorithm that essentially 1 plus epsilon approximate f of P in this space. So what's the meaning of that? It means that for P greater than 2, actually the best space that you can get it is m to the 1 minus 2 over P, and this is tight. So it is a tight result. You cannot do better than that, and there is an algorithm it can do. So here, you can actually, these are the proofs. You can go to the paper to see the things. Here, I want to give one example of them. And here, these are all similar, the things that we have seen it here. And here, this is the one that specifically is used for F infinity. So let's see for the F infinity, and how can we use the disjointness dispar instead of the index problem. Yeah.
So here n or n is the length of the string or the size of the set.
So m is the range that these guys are coming. Oh. So these guys, they were coming from 0 to m minus to m. This is like a thing. They come from 0 to m minus 1, and there were x1. So the original one was y1 to yn. And then we compute xi's, which are the frequencies, and then based on xi's, we are defining the frequency moment.
Are we also assuming that n is at most polynomially large as m?
So that's the. I am not so sure that is needed, but you can check the paper. I mean, I just mentioned this proof here. You can check whether we can check whether it is needed or not.
Yeah, because I think that if n is like probably exponentially large, then n, then like you need as many space to write down the answer, right?
So yes, I mean, yes, you are right. So that is correct. So in some sense, I mean, we are assuming m and n are polynomial. Otherwise, as you mentioned, so if n is much larger than this, you may actually count everything and you don't have these issues anymore. Yeah. Okay. Yeah.
Zero and one, like it's clear that the problem is easy. Why is the problem easy for p equal to 2?
So it's a non-trivial algorithm. So you can take a look at it. Yeah, I mean, this is non-trivial. For y between 0 and p is 0 to 2 is easy. It's not easy.
0 and 1 for 0 and 1.
Between here note that it is not 0 and 1. Any number between 0 and 1 you can also consider. P can be, I don't know, half, for example.
Oh, okay.
So p is not necessarily an integer. So this is for any p between this. So it's not just 0, 1, 2. It's any number between 0 and 2. Any like fractional number. You can see the paper actually for that. Good. Here, we want to say what we want to prove here. Good. Here we want to say that any randomized streaming algorithm. One other thing about disjointness is that works even for randomized algorithms. So that is stronger than. I mean, that case also strong. Actually, I think for index also you can get some randomized hardness as well. But here it gives. So if you can use the disjointness, you say that it is as hard as disjointness, then gives you, because it can also say for multipath and others. So. What do we want to say? We want to say any randomized streaming algorithm that computes f infinity requires order omega space. Good. So here we want to give a reduction from disjointness. And we know that any randomized algorithm, any randomized protocol for computing disjointness requires omega n. So then we get the results. But we need to show how can we, this then f infinity, this essentially frequency moment for p equal to infinity, that actually solves the problem for disjointness. So what was that problem for p infinity is that just like when f of infinity is that what is the max xi, correct? What is the maximum frequency? That's the one that we want to compute. Now, let's see this one. So let's consider this one. What are the disjointness? For disjointness, we have this essentially this Alice and Bob. And this is Bob. And these are the essentially she has like x1 to xn. And Bob has y1 to y. Good. Let's define for Alice those indices, the set of indices which are equal to 1. Good. So for Alice, say these are the set of indices that So what are these? The set of indices that xi is equal to 1 for us. That would be the set A. So from this guy, we create a set A. Then let's see for Bob. For Bob, also define B as the set of indices that yi's are equal to 1. So from Bob also you can do that. Good. Now, we are, what is the streaming algorithm that we want to give it? We are first giving essentially A, and then good. So this is the this is the way that essentially assuming that there is what is the thing? So we are assuming that there is some like a streaming algorithm that can compute f infinity in order omega s. So what is here? The question is that what is m here in this case? So m would be essentially equal to n, correct? Because these are all these a and b are the indices, and the indices would be between 0 to n, or n minus 1. So m and n are the same here. And again, a is a set of, this is important, a is a set of indices that xi is equal to 1, and b is a set of indices that yi is equal to 1. So for any I that yi is equal to 1, I will include it in B. Similarly for A. Now, assume that there is a streaming algorithm that can solve this problem, can find the disjointness, this f infinity in little of m. And as I mentioned, m and n are the same. So what do I do? In this case, I will give first A to this algorithm. This is the algorithm. Then I will give, then see what is the memory at this time. This memory is the one that I send it to Bob and ask Bob to continue that with the B indices that he has. So Alice has A, runs the algorithm on A, gets the memory, and then gives this memory, this is the thing that communicates to Bob, and Bob runs the algorithm on the memory with the set of indices B that. Now, at the end, so this is the important thing. So here, this is the case. X infinity is equal to 2, like X is equal to 1, if and only if A and B are disjoint. And 2 otherwise. So, so if there is one index that both of them have the same number, so then in that case it would be 2. So xi would be 2. If there is no such index, it means that both of them are disjoint. So now here, so as I mentioned, so for this stream, either 1 or 2, I mean, whether f infinity is 1 or 2, depending on whether these are disjoint or not. So they can decide, Alice and Bob can determine whether the sets are disjoint using the output of this algorithm. Not only that, this algorithm actually, again, this one says that even 2 approximation of that is hard. Because, so what is the hardness? The hardness, again, between the case between 1 and 2. So you cannot have even no algorithm better than 2. So there is, in some sense, no algorithm with approximation factor better than 2. Good. So it says that not only we cannot find f infinity with little o of m, but there is no true approximation of f infinity also with a space little o of m. Why? Again, the same reason that I have mentioned for that 5/3 things. Because if there is any approximation better than 2, we just see what is the output of this algorithm. If this algorithm is essentially anything better than 2, it means that it should be 1. Because the approximation factor of this algorithm is less than 2. So if it is something less than 2, it means that it should be 1. If it is 2 or greater, then we know that it cannot be 1, it should be 2. So that's the things that this one essentially gives us. So here, as I mentioned, so there is no 2 minus epsilon approximation actually here. And this above algorithm works even if we want to say that if this guy is the multi-passes on the input. So it might be the case that this input, they go back and forth essentially, because you can say that when you go back and forth, you can, because the disjointness actually is hard even for any constant number of communication rounds. The total communication should be ordered. That turns into essentially p passes. So we can say that if there are like the p passes in the input, so you are going p times, the total things that you are giving the communication would be p times c. C is the size of this memory. So that says that essentially if you have even p passes on this input, still you cannot get better than 2 approximation for f infinity. So that's the good things about the disjointness problem. I mean, another example, you can actually try, this is one thing for as an exercise, the disjointness for maximum connectivity component. So any multi-pass streaming algorithm solving maximum connected component, the same problem that I mentioned at the beginning, on forest needs order n memory space, even for multi-pass streaming algorithm. So as long as you are doing given constant number of rounds, still you cannot get anything better than that, because of the disjointness. So if you can get the results from disjointness is strong, so that multiple times you can communicate, and still the sum of this should be at least omega. It means that the total memory that this multi-pass algorithm can do it would be at least. And so that would be very similar to that reduction. I mean, the thing is that the same thing that we have discussed previous time about the disjointness. We are just using disjointness instead of index, and this is a hint that I'm giving essentially, that we had Ri to Di is equal to 1 if and only if Yi is equal to 1. We can go and check it, and that's a good exercise actually. Great. So, okay, so there are some more hardness that I will actually talk about them next time before presentation. And then I think we are done for now. Any questions? So we have a 3 presentation next time, and then we go from there. Okay, thanks, and bye for now.